We have a last level cache of 1 megabyte, 16-way associative, with a 1% miss rate. We are going to partition it 50-50 across two applications. Application A has a miss curve that halves once it goes beyond 512 kilobytes, while application B has a flat miss curve with respect to capacity. We will compute the throughput impact of a 50-50 split, and then argue for utility-based partitioning using both math and a picture. Let's set up the problem on screen and state the working assumptions we will use to quantify throughput. To turn miss rates into throughput, we will use a simple and standard model. Assume each application runs on its own core at the same clock with a base cycles per instruction of 1.0, a last level cache lookup rate of 0.5 references per instruction, and a main memory miss penalty of 200 cycles. We will compute cycles per instruction as base plus reference rate times miss penalty. That is CPI equals CPI base plus R times M, RI times MP. We will also assume that at 1 megabyte app A has 1% miss rate and app B has 1% miss rate, consistent with the given overall baseline. When app A is limited to 512 kilobytes, its miss rate doubles to 2% because its curve halves when you go above 512 kilobytes. App B is flat at 1% regardless of capacity. First compute the 50-50 split. Application A at 512 kilobytes has miss rate 2%. Application B at 512 kilobytes has miss rate 1%. So CPI A equals 1 plus 0.5 times 0.02 times 200, which is 3.0. And CPI B equals 1 plus 0.5 times 0.01 times 200, which is 2.0. Instruction throughput per core is the reciprocal of CPI, so IPCA is 0.33. IPCB is 0.5. Total throughput equals 0.833 in normalized units. Now, consider utility-based partitioning. Because application A gets a big reduction past 512 kilobytes and application B is flat, give more cache to A, for example 768 kilobytes to A and 256 kilobytes to B. This places application A above the 512 kilobyte knee, so its miss rate is 1% and application B stays at 1%. Then both CPI values are 2.0. Each IPC is 0.5, so the total throughput is 1.0. The throughput gain over the equal split is about 20%. Let us visualize the miss curves. On the horizontal axis, we put allocated cache capacity from 0 to 1024 kilobytes. On the vertical axis, we put miss rate. We draw application A in blue. It sits at 2% up to 512 kilobytes, then drops to 1% above that. Application B in red is flat at 1% across all sizes. We mark the 50-50 split at 512 kilobytes for both. Notice A is above the knee there. Now, we mark the utility-based split, A at 768 kilobytes and B at 256 kilobytes. Application A moves to the lower 1% shelf, while application B stays at 1% since its curve is flat. This picture makes the utility argument clear. The marginal benefit of capacity is much larger for application A near the knee. Let us compare throughputs side by side. The equal split achieves 0.833, and the utility-based split achieves 1.0 in the same normalized units. That is about a 20% improvement by assigning cache where it has higher marginal utility. Why does utility-based partitioning win? Because it considers the marginal utility, which is how much miss rate drops if you give a little more cache. Near 512 kilobytes application A has a large drop, while application B has almost zero slope. Allocating extra capacity to A reduces total memory stall time the most, raising overall throughput. This argument is independent of associativity here. The 16-way detail is not changing the knee we modeled. In short, give cache to the application with the steepest utility at the current split. To summarize, the equal split leaves application A above its knee and wastes potential performance. Utility-based partitioning shifts cache to the application that gets the biggest miss reduction, reducing total stall time and improving overall throughput by around 20% in our numbers. This is the power of utility-based partitioning. Allocate where the marginal gain is highest.